Unmuted. Welcome, welcome, welcome. Just giving us an extra minute or so while people join in. While we're waiting, if anyone feels so brave to try the Q&A feature and at least let me know through a question that you can see and hear me, that would be wonderful. Thanks, Felix. Excellent. Very good. Fantastic. Thanks, Theodore. All right. Okay, excellent. Thank you, everyone. I think we're good. I might ask you, we can stop using the Q&A feature now, only because I have to clear this stuff. All right, thanks, everyone. Awesome. I love it. All right, I think we are probably good to go. People will join as we go, but let's get started. So, for a topic that is maybe a little niche, I was blown away by how many people registered. I checked about an hour ago, we're a little over 350. So I'm super excited. Thank you so much. I'm glad, like I see it all the time in my work, how big a blocker statistics is for a lot of people and teams in experimentation. So I just wanted to share and thank you all. I hope you find this useful. Let's do it. And it sort of starts right with this, right? If you work in experimentation, you work with statistics. Like it's just a fact of life. There is no getting around this. We use statistics to compare variance, right? When we run an A/B test or an experiment, we've got, say, control and test. We're trying to use statistics to help us compare the two. And because we do that at the end of the experiment, we also can use statistics to plan for good experiments. So there's a lot of statistics around. So it's sort of a bummer when you join the field, you just get thrown in if you haven't had formal statistics training and just expected to figure it out. And statistics can be hard and for some people a bit boring, but I don't think it's boring. I love it. But I do think it can be hard to teach because it's quite a technical topic. So I understand why people find it boring, like professor, like lecture style in an old school university. Learning formulas is not fun. So luckily, for some very weird reason, I really enjoy teaching stats and I like teaching it in a non-technical way. And so thank you for trusting me with your stats skills today or when you watch this recording. And if you didn't know already, which I assume you did, my name is Simon. A little background just so you understand where I'm coming from. I was once a scientist. I have a PhD, hence all my socials and everything saying Dr. Simon Jackson. It just sort of stuck. And that was in a field of psychology that was very heavy on research method and statistics. I transitioned into data scientist and I ended up on the experimentation platform team at Booking.com in Amsterdam. Then I worked through a various bunch of data science management and then product leadership roles across big tech, so across Meta and then Canva. Presently, I'm an independent consultant with a mystery asterisk there. And you'll see I've just worked consistently in statistics and experimentation and growth through my career. Also, just a reminder, the recording will be sent soon, so not immediately after this. It's my evening, so wherever you are in the world, good night, good evening, good morning, good afternoon, whatever it is for you, but I'm probably going to go to bed after this, so I'll send it out tomorrow. And if you're here live, you can use the Q&A function, which I believe lots of people have been using, checking for me already, so it seems to work. I will check it periodically, so not instantly, but at certain breaks, I'll give it a check. So feel free to use that if you have questions as we go. Today, it's a pretty long session, but the idea is to try and give you like all the fundamentals and you can come back to this. I think it's important to carve out some boundaries, like what is this webinar about and what isn't it about? We're going to briefly touch on why we use statistics in experimentation. It's sort of a thing that no one addresses in the first place, and it's really important for setting us up to understand statistics. Then the bulk of the webinar is going to be understanding how does statistics work when you run an experiment and you compare results, so you can look at results confidently and understand what's going on. And then the last part will be how do you use statistics to plan great experiments so you have a really good chance of figuring out if there's a change or an effect between testing control and so on. And we'll do things like power analyses and so on with calculators, and that'll be super practical. So we'll start with the boundaries of this webinar. Today is about, by and large, the most common setup, right? This is really important. I'm exclusively talking about situations where you have a two-variant experiment, A/B, control test, with a 50-50 split. I'm talking about the most common question you would ask with statistics of a given metric, which is test different from control? And I'll be talking about the most common statistical tests that get used. Don't worry if you don't know what this word frequentis means, but if you do, you might see things like Bayesian or bootstrapping. These are other types of statistics. We're not touching those. So we're dealing with like the thing that probably 90+% of cases deal with in the land of experimentation and A/B testing. The principles still do apply and are still super useful if you find yourself outside these boundaries. So it's still very useful, but just know that this is the constraint. Also, in terms of how I'm teaching this and how I like to teach, I really prefer to try and share concepts like intuition and things that can glue in your mind more than trying to give you formulas or statistical precision. So if there's any statisticians who've snuck in here to nitpick my content, you're in bad luck, because that's not the point. I'm not here to give everyone a like perfect statistician perspective of the world. I'm trying to share things that are going to be practically useful for you. We're going to cover core concepts, not everything. Statistics is a massive universe, hence the background of this slide. And I do suggest treat this as like an intro. It's even though hopefully a lot of this does glue in your brain, a lot of it will not. It's a long session, so think of it like an intro and come back to it every so often, and slowly the concepts will really solidify. Yeah, the little arrow to the star here is meant to say like we're dealing with this one point in the universe of statistics and experimentation, but it is a really common and important point. All right. Why statistics? I really like to address this question because, like I said before, you get thrown into experimentation and you're just like, someone says, yeah, we use statistics. Here's a p-value, here are confidence intervals, blah, blah, blah. And you're like, first of all, it doesn't make sense. Second of all, why? Why do this? And no one really has a great answer. I will give you my answer, and I hope it feels appropriate. So there are two reasons when you run an experiment, an A/B test, why you might see a difference between the variants, between control and test, right? There are just two core drivers of that difference. And you don't have to answer, just think for yourself, like, what might those be? Signal and noise. This concept is absolutely critical to understand. This is why I start up front with it. Signal and noise. So, signal refers to any meaningful differences you can learn from, right? That's when the change you've introduced, say, to your product or to your customers, is actually truly generating a change in the world, a change of behavior, a change in revenue, whatever it may be. There's something real here. And if you were to repeat this experiment many times, you would consistently get similar results, like similar uplifts, for example. That's signal, something real. Noise, on the other hand, is just totally random differences. It's just like random stuff. It's not consistent. It won't replicate. It's just random. And we very much try to avoid reading into this. So we want to find and understand signal. We want to learn from signal. We want to just not worry about noise and push it aside. The challenge, and why why experimentation and innovation as a thing is hard, is because all results have noise. Every single experiment, A/B test you run, there is noise in the results. Even when you run AA tests, and just in case if you're not familiar, an AA test is an experiment, an A/B test, where control and treatment get exactly the same experience. There is no difference there. And if you're interested in why, I just published a newsletter on this, but even when you run AA tests, you still never get exactly the same results in control and test, right? You will never get the same, say, conversion rate in control and test, even if there's no difference in their experiences, because there's noise. It takes one person in one group to make that extra purchase, and they're slightly different. just purely by chance, right? So all results have noise. It is ever present. Only some results have signal, right? Only some of the things we do actually have an impact on our customers and our business. And so the challenge that we face when we run an experiment, let's say this represents conversion rates, like percentage conversion rates for control and test across a few experiments, and you can see that the gap between control and test is getting bigger and bigger. Like, where do you draw the line? Where do you say this is a case where it's just noise and control and test are probably the same, or there's signal here and I think there's a real difference? Like, where do you draw that line, right? And I guarantee you, if you give results like this to 10 different people, you will get them drawing lines at 10 different places completely. Or if you give the results to the same person at 10 different times over 10 different days, they'll draw the line differently 10 different times. And whereas statistics gives us the technical saying here is valid and reliable way to make this decision. Valid meaning it is pretty damn accurate in its call. And we're not diving into this, but that is based on a ton of probability theory and mathematics, which helps statistics to optimize where that line should be, right? That's one thing you just have to trust me on in this webinar. But if you want to get super deep, then that's a follow-up. And the other thing, it's reliable, it's consistent. You give it the same set of results, you will always get the same output. It's never going to change. And so another way I like to phrase it in a way that's practical in our like daily work is we use statistics to make this decision between noise or some signal with accuracy. It's an accurate approach and alignment, right? It lets lots and lots of people agree on where that line should be because it's a shared approach. That's my explanation for why we use statistics. Great. Now, I will quickly check, probably not, I'll quickly check Q&As. No, nothing, very good. This is where we start getting really into the meat of understanding statistics in experimentation. So this section is going to dive right into when we run an experiment, we get results like how does statistics figure out where this line is? What are the levers that move results around? And then how do you actually see these results typically presented in experiment tools and platforms? And how do you make sure you're understanding what's going on? Like I said, imagine you've gathered your results. You've run an experiment, you've gathered results, whether it's conversion rate or something else. How does statistics make this decision, right? It's trying to help us decide whether the difference between the two groups is just random noise or there's some signal in there. To do that, it uses these things. 3 pieces of information or 3 data points, a core assumption, and 1 rule. You probably know about these intuitively already, even if your brain isn't connecting the dots right now. But you'll see as we go that they're all probably concepts that you're familiar with, you've just never put them together. So we're going to build up our intuition. We're going to start with what are those 3 data points that statistics uses? Now imagine you work at Amazon. Apparently this was a test that got run. There's a link in the slides you can check out later. But imagine you ran this button color test. And let's say you ran it 3 times. The table here shows the results of this test each time, test 1, test 2, test 3. You have in these columns the average order value for customers in the control condition, the average order value for customers in the test condition, and one other piece of information. Have a read through. I'm going to go silent for about 20 seconds and think to yourself, is this difference between control and test noise? Or is there probably signal? And think about the information your brain is attending to. All right, I'm going to pick it up. Also, I got to say, I usually run this session live, and it's super weird as a webinar where I literally can't see anyone. But I hope you did some reading during that awkward silence. So let's pull this table across. I'm going to use each test as a way to showcase the sort of information that statistics uses, the three pieces of data that it uses. So in test one, the average order value of control and test were $100 and $110. Okay. Is there a $10 lift, 10% lift? Maybe. But then you look and you see, oh, there's only 10 people in each variant. That's nothing, right? Most of us intuitively get this. Like when you have very few people, there's lots of noise around, right? Statistics gets this. Statistics uses this information. It uses sample size and it works it out like in the way the formulas are constructed. It says when you have a small sample size, it assumes there's more noise in the results. So sample size is the first piece of information. You're probably very well accustomed to thinking about this. Now in the second test, I bumped up the sample size, but really brought the average group differences closer, right? $100 and $102. And so you might have gone, well, sample size might be okay, but like that's a pretty small difference now. I'm unsure. Again, statistics uses this. It's called the observed effect, right? This is the observed difference between control and test. And the way the formula works is it assumes that signal tends to produce larger differences, right? So when differences are small, it tends to come from noise. When differences are larger, it tends to be produced by signal. And the last data point is this thing called variance. I'm going to explain it. There is a link later to a video that goes deep, but I'll try and quickly cover it here. So here we go back to the 100 versus 110. But here I said the largest order in control. So even though $100 is an average, the largest in control was only $103. That's pretty tight. Like that's a tight clustering of customers around that average, right? And so what the statistics is looking at here is how spread out are your customers just from each other, not thinking about control versus chest, just from each other. And when there's a lot of spread between customers, there tends to be more noise in those averages. So think about two cases here, right? If the range of customer orders in control was $95 to $105, that's pretty tight. And you'd probably think, wow, getting to $110 is a big deal. But what if that range was $5 to $5,000? Now that $10 difference sort of seems washed out in all that variation, right? So that's what's going on here. Sample size, the observed effect, and variance in the metric. I just noticed a question. Yeah, perfect. Yeah. Thanks, Satyajit. Also, forgive me if I mispronounce your name, but you're right. I'll just dismiss this to keep that fresh. Okay, so statistics uses these three data points to calculate the probability that the differences between controller tests are just noise. That's what it's doing. It's putting these three things together in a formula to go, what's the probability that it's just noise and not signal? That's what it's trying to do for us. Now, to say group differences are just noise, that's more probable in a situation like this, when you have low sample sizes, low observed effects, so low difference between the groups, or very high variance. When you have one or all of these things, it tends to be the case that any difference you see between control and test is very likely, right? It's more probable. But this flips and this becomes less probable in the opposite scenario, right? When you have a very high sample, there tends not to be noise. When you have very high observed effect, it tends to be signal. And when you have very low variance, there tends not to be much noise, right? So this is how these three things conceptually work, right? And push the statistics to help you decide between these two things. Now you might have noticed the word probability just came up a lot. It's sometimes a bit of a scary word. I totally appreciate that. But this is where the term p-value comes from. I'm assuming if you're in this webinar, you do A/B testing, you've sort of had to deal with statistics, you've probably heard of this term p-value. I don't think anyone really explains it very well. I'm not going to explain it the way a statistician would, but I want to give you the intuition for it. it's exactly what we talked about, right? It's statistics using these three data points, sample size, observed effect, and variance, to calculate P as the probability that it's just noise. That's pretty much it. So I'm going to give you some questions. I'll just give you like a few seconds to think about each of them. What does a p-value of 0.9 mean? Right? If you have this experiment and you get this p-value from the statistic, what does that mean? That means the probability that this difference is just caused by noise, it's just a random difference, is about 90%. That's pretty high, right? That's probably a situation where you go, yeah, it's probably just noise. There's probably nothing going on here. What about 0.1? It's the other end of the scale, right? That's saying the probability that the difference between control and test is just noise is only 10%. That's pretty low. That means it's much more unlikely, and you might start be moving into the territory of maybe there's signal here. What about a p of 1.2? So you could interpret it, right? The probability that it's just noise is 120%, but this is actually a trick question. The probability cannot be over 100%, right? It can't be more than 100% probable that it's noise. So p-values cap out at 1, right? I thought this was really important to include because I once saw someone playing around with like their ChatGPT and it like hallucinated a p-value over 1. I'm like, this is really important to understand. What about a negative 0.3? So if you just say it, it's saying the probability that it's just noise is negative 30%. Again, trick question. Probability cannot be less than 0. So p-values can't be less than 0. So p-values range from, 0 to 1, where 1 means this is 100% noise, and 0 means this is 0% noise. This has to be signal. You're never going to get 0, but you're always going to get like 0.0000 something in a really great setup. All right, let's go through some examples with some real data points so you can see how each of these three data points shifts that p-value up and down. We'll start with a baseline setup here. Let's say we run an experiment where our sample size is 350,000 customers in each variant in control and test. The observed effect, let's say in control, the average order value is 10, and in test it was 10.1, so it's going up from 10 to 10.1. And the variance is measured with standard deviation of 20. I'll come back to explaining standard deviation, but just quickly, it's a measure of variance, like how spread out customers are when you have a continuous metric, like average order value. It's a little bit different in binary. I'll talk about that later. I'm just using it here because it's a standalone thing, which is a bit easier. But I do have a YouTube video that goes like really deep on it if you want to really wrap your head around it. Okay, so with this setup, your p-value is 0.04, right? The probability that it's just noise is only 4%. That's pretty unlikely. What happens if we keep everything the same except really, really reduce the sample size? That p-value now shoots way up to 0.91. The probability that it's just noise with a sample size of 1,000 in each variant is 91%. Okay, this is almost definitely noise. All right, if we keep that flat, but now we try and increase, we say we actually observed a bigger effect. So instead of going from 10 to 10.1, we go from 10 to 12. That's much bigger, right? That's a 20% relative increase. The p-value drops way back down, right? Now it's back down to 3%. And finally, if we shoot that standard deviation up, so we're saying customers are way more spread out, the p-value goes back up, right? It becomes more likely to be noise. So I hope the concept, the idea behind this slide is you can see how moving each one of these things causes the p-value to go up and down. So we've covered these three data points, sample size, observed effect, and variance. We actually did cover the core assumption, but very implicitly, very subtly. Did you catch it? It's this. It's the assumption that there's only noise. And it's a pretty safe assumption. If you had to make an assumption, right? If you had to say, without seeing any data, do I think it's just noise or that there's signal? saying it's just noise is the safe bet because noise is in everything, right? Remember that? There is always noise. Signal only sometimes. So it's a safe assumption. And so statistics is testing this assumption. The p-value is a test of this assumption. It's saying the probability that my assumption that it's just noise is correct is blah. That's why lower ends up corresponding with signal. Anyway, this is not like, don't freak out if this particular assumption is going over your head. It's probably the least important thing to remember, but I do want to include it here for completeness. Okay, what's way more important for everyone to understand is the one rule. So 3 data points, the assumption, and the rule. What is this rule? Remember, we're trying to make a decision here. We're trying to decide, is the difference between control and test just random noise? Or is there something real happening here that I can learn from? But we have a p-value that goes between 0 and 1. We have this like decimal thing. That's not a or B. And to get that decision, we need a threshold, right? We need a threshold to tell us that this p-value is so low, it's so unlikely to be noise. Let's call it signal. Oh, it looks like I duplicated a slide and forgot to delete the last one. Right. This is the threshold, right? So we have our p-value scale and we draw a line in the sand effectively and say, if the p-value is below it, it's so low, it can't just be noise. It's got to be signal. It's got many names, this threshold. You might hear of it being called a significance threshold, or the statistical term is often an alpha criterion. Don't stress if you haven't heard those. Probably what you're most likely to have heard is someone say p is less than 0.05. I'm guessing you've heard something like this. And that what they're describing is a threshold. They're putting a threshold at 0.05. And that threshold comes from either you making a decision, or it's been set, if you're not sure where, sometimes it often gets set by default in the statistical tools you're using or the platforms that you're using. So it's probably worth going and checking if you are unsure what it is in your platform or your tools. So let's think, what does p of less than 0.05 even mean? Right? We can just interpret it the way we've been referring to a p-value. It's the probability that the difference is just noise is less than 5%, right? It's 5% or less. That's like 1 in 20 or more. That's pretty rare, right? So that's why p of 0.05 is typically an industry standard, because 5% is a pretty rare thing. Less than 5% chance is pretty rare. It's rare enough that it's probably worth us saying this is signal. So when our p-value falls below that threshold, then we go, it's unlikely to be noise. Let's decide it's signal. And that's what we call statistically significant, right? Statistically significant means your p-value has gone under the threshold and you are making the decision that the difference between test and control is because of signal, not just noise. Obviously, the flip side is when the p-value is above the threshold, you're saying, you know what, it's probably just because of noise. And this gets called a bunch of things. Statisticians will say non-significant. Now, very quickly before I turn this into a visual, is the p-value, Prince asked, is the p-value same as alpha value? So the alpha value, Prince, is the threshold, the significance threshold. So that p of less than 0.05, or where I drew that red line, that's typically what the alpha value is called. Good question. Okay, so let's say we have this scale of p-values here, and we draw this threshold, this alpha value, this alpha criterion, significance threshold at 0.05. So we're saying p is less than 0.05. Basically, any p-values above the line, we declare as noise. Any below, we declare there's signal here, right? And we call these things non-significant and statistically significant. That's where all these things fit together. So if we go back to this set of results that we had before, if we use the threshold of p is less than 0.05, right, you can work this out pretty quickly. We would say the first and third conditions are statistically significant because those p-values are less than 0.05, and the second and fourth would be non-significant, and we'd say it's probably just noise. Right. I hope that makes a few things click in your brain to understand how does statistics take the data that we get in an experiment to create a p-value? What's this threshold? And how do we make a decision between statistically significant or not and decide that there's signal? Now, say you've gathered your results, you've used statistics in all this way, you've compared against your threshold, blah, 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 and you're making a decision. Like, how do you typically see this information and decision visualized in testing platforms? I think it's really important to now connect these concepts to what you would typically see in the tools that you're probably using in your daily work. I'm going to go through the most common visual you will see. As you can tell, I'm very big into covering the most common case. If you don't see exactly what I describe here, chances are you'll see something similar, and I hope that there's a clear connection for you. But if not, you can always write to me later and send me a screenshot in all honesty, and I'll explain it. And if I can't explain it, then that's a problem. The first thing you will almost always see when these things are visualized is like a big fat line with 0% written, which means this is where there is no difference between test and control, right? It's saying there is 0% difference between test and control. Right? This is that magical case I talked about at the beginning where the results would be exactly equal, which like never happens. You then see the observed effect line as a second line usually, and that represents the difference that actually showed up in your experiment between test and control. It's often reported as a relative percentage, right? Meaning 2% on top of the control baseline. So for example, if you are using conversion rates and your base conversion rate is 10% and your test condition conversion rate is 12%, that's an absolute change of 2%, but it would be usually reported in tools as plus 20% because it's 2% of 10%. So anyway, just something to remember. It's usually presented as a relative percentage. You then often see this bar around it. This is called a confidence interval. It is a representation of how much noise the statistical formula thinks is in your results. It is a combination of your sample size and the variance, right? How spread out customers are. It gets smaller when sample sizes are bigger or variance is smaller. And we'll come back to that. So don't stress about remembering that. But that's where all these things fit in. Now, a non-significant result, right? When your p-value is above your threshold and you're making the decision that it's probably just random noise, it usually looks something like this. It's like there's a gray bar, and the really important thing here, because this is not always the case, the confidence interval goes over 0. This overlap here instantly tells you this is a non-significant result. I have seen some tools where they'll like color one side and the other side different colors, like red and green. That is nonsense, provided you're using this approach to statistics. It's just confusing in my opinion. If the bar goes over 0, that is non-significant, right? The confidence intervals relation to 0 and whether your results are statistically significant are connected. They always mean the same thing, right? So it's often a gray bar or something neutral and goes over 0. When you get a statistically significant result, the first hint is that the confidence interval is now not going to overlap with 0, right? Whatever color it is, it's not overlapping 0. So in a case like this, you know it's statistically significant. That means the p-value has fallen under the threshold, and you are saying, well, the statistics is telling you to decide there's probably signal here. It usually goes a positive color like green when the movement is desirable, meaning the metric has moved in a direction that you want. So let's say conversion rate going up or revenue going up, that will go green. There are metrics where going down is a good thing. For example, page load time, right? Generally, you want your page to load faster, so to the left would be green. Or cancellations, for example. So that's why I use the word desirable here, because that color coding depends on what you say is good for your metric. But the key part here is statistically significant means it's outside zero. The reverse is undesirable, also statistically significant, so we're not including zero. It usually goes a different color like red. Again, it could be to the left, it could be like going negative here, which is common for a lot of metrics. It could be positive in the other direction, like the examples I gave before. It just depends on the metric. And the last thing you might see, depending on the tool or platform you're using, is some other bunch of colors like purple or something. These tend to be when you have a statistically significant result, but you don't have an opinion on which direction is good for your metric. Classic example is time on page, right? You might go, well, I'm interested in measuring time on page. Going up could be a good thing. Maybe that means someone's more engaged with the product, but going up could be a bad thing. Maybe they're confused and they don't know what to do. So I'm just not going to say whether up or down is good or bad. I just want to understand if it's moving in a particular direction. So that's sometimes what you see. This is an example from my Power Calculator, which we'll use later, where you can plug in test results and get answers. And you can see over here are these results. So here's the zero line. You have the uplift between test and control, and you have this confidence interval. You can see here it's outside of zero, so it's statistically significant. It's gone green, meaning it's positive or a desirable improvement. And you have all the other statistical stuff down here. And this is where you get your inputs and the visitors and conversion rate. And here's where I've said actually higher is better. And that's why it's gone green by moving to the right. I'm just going to check the question from Theodore, maybe a question for later, but I have a recent non-inferiority test where the entire CI sits below my set non-inferiority margin of -3%, yet it's not significant. Why is this? Okay, this is a slightly more advanced topic, Theodore, and I'm not going to cover it entirely here because it will probably go over a lot of people's heads. I'll give you something quick, and then please feel free to follow up with me later. The key thing here is that if you've set the non-inferiority margin at -3, non-inferiority tests are called one-tailed, which means they only go significant by moving in one direction, not both directions. So this is where it gets a little complicated. So if you're expecting it to sit, you want to check that it's not worse than -3, that it's above. It will only turn significant when it sits above -3, not below. I hope that helps. But like I said, follow up with me later if you want to learn more. All right, I'll do. Oh, cool. Thank you. My pleasure. Sarai, I'm going to leave your power is coming into the second part of the course. So I'll clear your question. I promise we are going to dive super deep into power. But I'm glad you're thinking about it. All right, let's move on. Right, one last view. It's very common to see an over time view like this. This is becoming more and more common in testing platforms, so I thought it would be useful to include. You might see something like this. If you're wondering how this connects to all the concepts we've been covering, it's this like little view that I've been talking about, rotated on its side, and then it's like snapshotted, usually like every day, and then plotted in a connected way. So this is saying the confidence intervals are overlapping zero and the results are non-significant all the way up to like day 9 or 10. And then suddenly the confidence intervals sit above zero, which is desirable, and it turns green and it's saying it's now statistically significant in a desirable direction. So if you do see this sort of view, that's what you're seeing. Right, take a breath. I am going to quickly answer Prince's question in the Q&A because it is free. Actually, I'll provide you with the URL very soon. And also, I would suggest this is a great time to take a breather. We covered a lot of like pretty dense statistical stuff. And now after this, we're going to move into things like errors and power and planning, which there have already been some questions about. So I'm going to pull up a timer. I'm going to hit a 5-minute break for everyone to use the bathroom, grab some water, whatever it is, and I will see you in 5 minutes. All right. Let's get back into it. Now, just during the break, I was answering some questions. If you're in the Q&A tab, you can pivot from like open questions to answered questions if you want to read through them. I'll quickly cover it off for the recording. First question from Prince was whether the calculator that I showed is free and open access. It definitely is. I'm going to share the link in the slides in a moment, but you can also check. I put the link in the answer to Prince there if you want to jump in even earlier. Bjorn asked what to do if, for example, two KPIs like conversion rate and average order value go up, but they're not significant. Can you verify whether there's still signal when it comes to total revenue? So there's an unfortunate reality in data and metrics and statistics that any the higher a metric you go, right, the more stuff you bundle together, the more noisy it tends to be. So if metrics like conversion rate and average order value aren't significant, they're non-significant, it's almost impossible the total revenue will be significant. But the best thing to do if you're in that situation, you want to check is compute total revenue as its own metric and run it through the statistical analysis. Nikki asked whether that timeline view we covered is different to sequential analysis. For those of you who are familiar with sequential analysis, yes, that time view is different from sequential analysis. I probably won't get into it here because it's complex, but I put a brief answer in the chat. Ben asked, will we be covering MDE, which stands for minimum detectable effect? 100%. This is going to be one of the big things we will talk about. And then I noticed there was one last question open from Andrea, however you pronounce your name, I'm sorry. Can you share some best practices to work with small sample size data to determine the signal versus noise? So I think that the sections we're about to enter into that are around power analysis will give you a lot of insight into the other levers you have to pull. If you're dealing with very small samples, and even those other levers don't help you, then you get into a world of more complex techniques. And if you find yourself there, I think the best thing to do is write to me, and I'm happy to share outside this course. Another couple of questions popped up, so I'll just answer these while we're here because we've got plenty of time. I'm using a different calculator. Where can I select one-sided or two-sided hypothesis testing? How is this relevant? So every calculator is a bit different in what it offers. For example, mine, I haven't added the choice to toggle one or two-sided yet. There are some out there that do. It is a more complicated topic that I probably will not get into here. But essentially, the idea is when you say two-sided, you're saying let the statistics go significant if the result goes in either direction in an extreme enough way. So I want to know if the metric's going up or down, you go significant. One-sided, you tell the statistics only go significant if it moves in a particular direction. Now it's going to get to statistical significance more easily if it moves in that direction compared to the two-sided. And that's probably the practical takeaway. One-sided means it's faster to get to statistical significance if it's moving in the direction that you are interested in. But if it's moving in the other direction, it's never ever going to be significant. Again, if you want to go deeper, best to follow up with me on that. Yeah, thanks, Tony. You are welcome. I'm glad. Satyajit, another question from you. How do you deal with trade-offs via statistics and not through business logic? For example, conversions go up, but average order value down. Perhaps not for this call, but we'll take it offline. Yeah, I mean, I'm very happy to answer that quickly because it's a topic I love. This is typically dealt with nicely by a topic referred to as the overall evaluation criteria. I don't know if he coined it, but Ronnie Kohavi is definitely, in my mind, the person who coined it, whether or not he did. But it's best to, prior to getting results and making a decision, set out a simple formula for yourself that determines how you'll trade it off, right? So like, for example, we're willing to get 10 more conversions for every dollar down on average order value, or whatever it is. Come up with a simple formula that helps you make that trade-off. That's really the fastest, easiest way to deal with it. There are more complex ways that we can certainly take offline. questions flying. Shristi, thank you. Will we walk through how to perform sequential testing? No, I'm sorry, Shristi. The sequential testing is a fairly complex topic in the world of statistics. I'm very happy to talk to you about it offline, but not in this course. But this should set you up with some of the foundations you need to understand it better. Jason, there are some very strong opinions on this topic, one-sided versus two-sided testing. Do you have any view on which is generally best, or does it depend too much on the testing scenario? No, it's all good. It's obviously of interest to people, so I'm happy to answer. I love answering this stuff. I've found that, and I agree, there are strong opinions, and I've ended up in some very weird debates with people like on social media, which I'm not a big fan of like doing. I don't think it's a good forum for it, and people get very upset about it. Personally, I default to two-sided, but that's certainly okay when you have enough what's called statistical power, which we'll deal with in a second. When you are lacking statistical power, so we'll get to it in a second, but you have like, for example, you have small sample sizes. That makes your life pretty hard. And so it can be a useful lever to understand one-sided and two-sided tests. So you might want to switch to one-sided where it's appropriate. Non-inferiority testing, which came up in a question earlier, that is an example of a one-sided test. So that's always the case. But yeah, I would say if you're unsure, default to two-sided. It's the safest thing because it's going to tell you whether your metric moves in either direction. And then if you feel like you're getting in a scenario where it's hard to get statistical significance, maybe go and learn about that. Nikki, thank you. I've not seen the tool do that view, and I don't know if a view like that made people peak more. Yeah. Yeah, so that view is usually to help teams who want to see the view I showed earlier. I can probably quickly jump back a slide. This view, I do see it in quite a few tools where there are teams who are looking at results not just on a given day, but they want to see patterns over time. So they want to see this consistent green because you can just get random spikes here and there. So it's very helpful to like look and understand how results are changing. It can also be a great view to pick up things like novelty effects, where you might get a big spike early on because users get confused by a new layout or something, but then drop down into non-significant, and that can be good when you're trying not to harm something. And or the opposite, which is effects that take time to build up. So it might be non-significant for a long time, and you'll see it slowly build over time, and it can be really useful for understanding these patterns. But yeah, Nikki, happy to follow up later. Jason, thank you. I'm really glad you're finding it useful. Natalia, what would you recommend to read for testing when there are network effects? Ooh, I don't know if I have a good reading. It's definitely a more complex topic, one I would love to talk about, but probably not here. The thing that comes straight to mind, which you might want to just look at, is switchback testing has become very popular for like marketplaces or riding services like Uber, where there's network effects. That might be relevant, but anyway, happy to follow up later. Oh wait, what are network effects? I'm assuming from the question, it's like when how you impact one individual has a flow-on effect to other individuals. But they can be complex. So all right, I'm going to clear them. Let's move on. We're about halfway. Yes, good. Oh, good. All right, that was the right answer, everyone. I'm being told this is what was meant. Excellent. Thank you both. All right, cool. Let's do it. So now we're going to get into how do we use all this knowledge and this statistics to plan great experiments. This is where we get super practical. So understanding how statistics gets us to results is important. Like it's very useful for you to know. But at the end of the day, it's most practical when you apply it to planning for your experiments. And we can do that because stats is used at the output, at the result side, and we know how it works, we can like reverse the math to preempt what might happen under different conditions. And that's what planning is all about. It's like taking the statistical formula and understanding how it works at the end and like simulating different inputs and outputs to figure out like what would happen. And that way we can get a good idea of what we should be doing before we even start an experiment. right? So for example, we know that sample size is one of the key inputs to statistical significance. And if we only get 100 users a week into our product or this area we're experimenting in, we know the p-value is probably going to be pretty high, right? Or getting a low p-value is going to be really tough. It's almost impossible to get a statistically significant result. So we just know not to bother. And that's sort of the logic here. And to get a little more specific, there is this concept I want to cover off before we get into power analysis, which is good planning helps us make fewer errors, right? And errors is a term that is technically used in statistics and experimentation. And understanding errors and why we do statistical planning is very important because it's going to help you run better experiments. It's going to help you waste less time. It's going to make sure that the things you're doing with experimentation are worthwhile and you're not just like running random things that are going to be non-significant or leading you in bad directions and ultimately either like take your business in the wrong direction in the worst case, or maybe best case is just people around you lose interest and trust in experimentation and then it just dies off in the company. So this is really, really important. We're going to understand errors first. So remember, statistics is giving us this valid and reliable way to make this decision, right? We covered that right at the beginning. Or as I like to say, an accurate and aligned way to make this decision. Now, just let's be clear. I said accurate, but I'm not claiming that statistics is perfect. It's trying its best. It's giving us the most accurate answer, but it cannot be perfect. And that's because of noise, right? Because there's noise, even in when there's signal, results shift around all the time. There is no perfect measurement. That's why we need statistics in the first place, because noise exists. And these mistakes, when there's a misjudgment between the decision of noise or signal, these get called errors. And there are two main ones. You've almost definitely heard the terms, but sometimes they might not lock into your brain. So I'm going to walk you through them. This is like the typical way they get explained. Imagine we could secretly know in reality whether the result is just noise or due to signal and noise, right? So this is like hypothetical where we have godlike powers and we know this in reality. And then we can see what the statistics is guessing between these two things. Obviously, when the statistics guesses the same thing as reality, that's a good thing. That's what we want. We want to maximize these cases. The other two are the error boxes. This box, when statistics is guessing that there's signal, but there's not, this is called a false positive. It's like sounding the alarm when it doesn't need to be sounded, right? It's like a doctor telling a man that he's pregnant, right? This is a false positive. We want to avoid this. The other box, statistics just thinking there's noise going non-significant, even though there was something there, that's called a false negative. And a lot of people get confused by this term. False negative. Negative here refers to like no alarm being sounded. So it's false. It's wrong. It's a wrong no alarm. The metaphor here being like, or the analogy like a doctor telling a clearly pregnant woman she's not pregnant. In terms of how the results like look, just to try and make this stuff connect in your brain, false positive means we're seeing a like statistically significant. We're getting this alarm. We're getting these bright colors, but we actually shouldn't have been. Right, these are like false alarms. They're big time wasters because you're like, oh, great, I found something. And then you just shoot off in that direction, making all these changes and following that line of logic, but there was really nothing there to begin with. False positives the other way. We get a non-significant, a neutral bar, whatever it might be, but we should have gotten a significant one. And these are like missed opportunities. There was something there, you just didn't catch it. So what is it that goes into planning experiments to minimize these things, these false positives and false negatives? Quite a few things, but one is we've already made a key decision that influences these things. If your brain has the capacity after all this dense material, think back and be like, what might be the thing that we decided, nothing to do with data points, we made a decision that influences these things. It's the rule, it's the threshold or the alpha criteria. And I'm going to explain why. Let's say we have p-values for a whole bunch of experiments, right? Every little flask or test tube here represents a p-value on this scale. And let's say we secretly, again, hypothetically, with our godlike powers, we secretly know whether there's just noise or signal and noise, right? Those blue ones are these four along the side here. And we draw our significance threshold at p is less than 0.05, like industry standard, right? Now you can see if we do that, these two would be false negatives. We're saying they're non-significant when they should have been. And this one would be a false positive. It's gone statistically significant, but it shouldn't have been, right? And maybe I, as a business lead, I'm like, I don't want to miss opportunities. I don't like those false negatives. Let's bump the threshold up. And so we bump it up to p is less than 0.1. Now I'm getting all those opportunities. There are now 0 false negatives, but I've got an extra false positive, right? And so you can see you can move your threshold around and you're just trading off between these things. Higher threshold means you're going to get more statistically significant results, like hands down. I mean, at an extreme case, imagine you set the threshold at 1. Every single result would be statistically significant. Now, that means you're going to have less false negatives, but more false positives, right? So more false alarms and time wasters. Conversely, when you reduce the threshold, let's say you took it in an extreme case all the way to 0, you would have no statistically significant results. So you're going to have less significant results. That means you'll let less false positives, less time wasters, but more false negatives. You're going to miss more opportunities. It is a risk trade-off for you to decide. It is not a math problem. This is a business one. Now, I think it's important to be aware of. The reality, though, is that in 99% of cases, you pick a threshold and you just use it all the time. And the industry standards are these two that I was talking about, 0.05 or 0.1. Like you'll find these in 99.9% of cases. So I just think if you're just learning about this for the first time, you're not even sure what you use in your work, it's probably worth going and learning about that. And if you want to get more advanced, this is a lever you have to pull in your business if you want, but just be wary, it's a trade-off. For the rest of the webinar, we're just going to assume a fixed threshold, right? We're not going to mess around with that threshold anymore. The key thing is, what about the p-value? How do we make sure that p-value is low when there's signal, right? How do we really maximize our chance of detecting signal when it's there and minimize it when it's noise, right? Make sure the p-value sits above the threshold when it's just noise. This is what we really care about. Remember, we're going to have a low p-value when our sample size is higher, our observed effect is higher, or our variance is lower. Like this is the combo that gets us to low p-values when there's signal. And I want to show you exactly how these play out in non-significant and significant results. So remember, this is the view we shared before. You have the observed effect as the line, and you have the sample size or variance defining the confidence interval. If the observed effect is higher, down here, you just notice the whole thing shifts and that confidence interval eventually doesn't include 0 anymore, and it becomes a statistically significant result, right? So if you can push the observed effect further away from 0, or you don't push it, but if you can get an observed effect much, much further away from 0, the whole thing is going to move. Let's shift back. The other way we can get statistical significance is by one of these combos. Bigger samples or lower variance. That doesn't move the whole bar, rather it squashes it and makes it smaller. And if it gets smaller and smaller and smaller, eventually it doesn't include 0 and you get a statistically significant result. So this ability to detect signal, right? The probability of being significant if there's signal, this ability to have large samples or large effects or low variance. This has a name. Some of you have mentioned it already. It is power. Yes. Sorry, I love this GIF because Chris Hemsworth is Australian like me, and I'm sure if I had hair, we might look similar. Maybe. I need to work out a little more. Anyway, power, statistical power, you've said it already. High power comes from these three things. High sample sizes, high observed effects, low variance, right? This is the golden combo we're trying to get. Great, cool. We all want more power. Every experimenter, whether they know what the term means or not, is trying to get more statistical power, but you don't get it for free, and that's the challenge. That's the problem of experimentation in reality. And so power analysis typically gets used as an umbrella term referring to a whole bunch of calculations that help us to plan between these levers given the constraints we face. Like the example of the question asked earlier, like I have small samples, right? That's a constraint. So you're stuck with that. How do I play around with the other levers to understand what I can do? So this is what I mean, or people mean when they're talking about power analysis. We are going to now explore how these levers work, and we're actually going to get practical and do our own power analysis together through one formula. I've got one formula in this entire talk. And it's really simple. I'm just converting that image that I showed before into the formula at the bottom. Power equals sample size plus observed effect minus variance, right? The way to read it is exactly the way you have it above. I have more power, higher power, when I have higher sample sizes, higher observed effect, or negative, meaning lower variance. That's how I read it. And the reason that I do this is because it's just a very basic formula. It's just plus and minuses, right? And so I'm pretty sure everyone here has enough math background to rearrange that. When you rearrange it, you can see how the various power analysis calculations work. So I'm just going to quickly take you through how this gets rearranged so that each of these terms, power, sample size, observed effect, and variance, gets its own spotlight. So the first one is sample size. This is saying we need a higher sample when we want more power, or we're trying to detect smaller effects, or our metric has more variance, right? That's how I would say this. We can rearrange it for observed effect. This is the minimum detectable effect one we'll come back to very soon. For me to detect, you know what, I'm gonna explain this one a bit later because there's something funny that's gonna happen, you'll see. And then there's a variance one. Actually, I don't use this one at all, but just for completeness, I put it on the slide. Let's get practical. So now we're going to put everything we've learned into practice to do power analyses. You are very welcome, and I would suggest trying to follow along. I'll give opportunities to actually play with numbers. You can either use your own power calculator, or you can use mine. This is a screenshot of mine. This is the URL. It's also shared in one of the answers. I assume your favorite is mine, not really, but I built this power calculator specifically after teaching this type of material many times and really struggling with some of the other calculators out there. So that's why I built this. So it's sort of designed to go with this material if you want to use it. But you can very much go and use your own or even compare the results between. That's not a bad idea either. So power calculations, level 1, planning sample size. The question here is when you're going into planning an experiment, you're like, how big a sample size do I need to be able to detect signal? This is like the most common question people ask at the beginning. So I'll bring us back to this version of the formula. Sample size equals power minus observed effect plus variance. Or the way to say it is, I need a bigger sample if I want more power, or I'm trying to detect smaller effects, or my metric has more variance. So where do all these things come from? Power, I am not getting into the details here because I think we've covered up more than enough technical content, but it is another threshold, just like the alpha criterion or the significance criterion, the P is less than 0.5. Power is another threshold. The industry standard is 80%. That means you have an 80% chance to get a statistically significant result when there is truly signal. If this is all going over your head, and that's totally legit, just take me at my word, stick with 80%. Almost everyone does. If you want to get really advanced, you can play around with it. But in my time doing this type of work, even in the biggest programs in the world, even being the data scientist on these programs at some points, you mess around with this maybe 1 in 1,000 tests. Like, just don't stress, just stick with 80%. Okay, where does variance come from? We know variance. You should know variance. It should come from data that you have about your metric, right? Do you have an analysis on how your metric behaves in the past? Have you run a past experiment and you can see your metric? From that, you should be able to get the variance that you're dealing with. I already mentioned for continuous metrics like average order value, this is a thing called standard deviation. If you're unsure what it is or how to calculate it, you can either go rewatch that YouTube video I shared before or speak to a data analyst or someone. They should be able to help you. Probably, I'm sure even like LLMs like ChatGPT are going to have a pretty fine time explaining how you can get that. For binary metrics like a conversion rate, the nice thing is the conversion rate itself includes the variance. I'm not going to explain why, but like if you have a conversion rate of 5%, that's all you need to know. You just need to know it's 5%. Cool. So you've got these two things. The big question is, what do we do with the observed effect? We don't know what the observed effect would be because like it could be zero. It could just be noise. That's why we run an experiment, because we don't know what this thing is. So here we're not trying to put in what we think the result will be. We're trying to put in what we care about. And this is called the minimum detectable effect. This is the smallest effect, the smallest signal that we want to be able to detect. And a lot of people ask me, like when I start to say this, like, but don't I want to detect any signal? So first of all, I hope by now you have an appreciation that you cannot detect any signal. Even statistics isn't perfect, right? The other thing is, practically speaking, you don't want to detect any signal, right? Let's say you run an experiment out described here where the impact to your conversion rate is like 0.00001% or something super, super tiny. Do you really care about detecting that? Like, is that really valuable for your customers in your business? Practically no. Right? It might be statistically significant if you have a big enough sample size, but it's not practically significant. And so you don't really care about this, right? It's not worth the time and effort you put into running experiments, the salaries that you and your team are being paid, the cost of all the technology and the infrastructure to make this happen. Like, it's not worth trying to find this stuff. On the other hand, maybe an impact of 10% would be epic. Okay, cool. We definitely want to detect 10%. So where's the line? Maybe 1% for your company. Like finding a 1% uplift is really good. This depends on your situation, right? So I cannot give you a definitive way to choose this, but I can give you some tips on how I see teams do it and things that work for them. So one thing is, like, if you have past experiments to lean on, just look at how much your metric tends to move. That'll at least anchor you in the realm of reality. Like, does my metric often move like 1 to 2%? Has it ever moved like that? Cool, then I can think about that range. But if it's only ever moved like 0.1%, then 1 to 2% is almost impossible, right? Another thing is, think of a celebration criteria. This is really nice. Like, what result would you and your team celebrate? That's a really nice way to think about what you care about. Another way is like, what's worth all the effort? Like, what's worth the effort about time and the technology and our salaries and blah, blah, blah. And like, what's actually worth it? Whatever you decide here, it's not a decision you want to make many, many times. It's like quite painful. So just, I would really suggest is like, go through the exercise maybe once and just try to align and set it across time and even across teams if you're focused on the same metric. So just stick to something. And just a useful tip is that the bigger your business, the smaller it tends to be, right? Because it's a relative change that people tend to talk about. So a 1% change to a scale up is very different to a 1% change for Google, right? So for Google, a 0.01% change is probably still bigger than a 1% change for a scale up, right? So the bigger your business, the smaller it tends to be. Right. So this last piece comes from you making a decision. We now have everything we need to figure out what sample size do we need to run an experiment. So I'm going to leave this on the screen, try and put it to the test. Open your power calculator. There's the link to mine if you just want to use mine. Here's some numbers you can play around with, like a binary metric with a base rate of 12%. power of 80%, and you want to be able to detect a 5% uplift, roughly what sample size do you need? Have a play around. I'm just going to have a look at the Q&A. Just while you guys are playing, I'll answer some of these questions live. So Thomas asked, how much a metric moves equals variance, right? How is that different? That's not true. So how much a metric moves, I mean, if you're talking about like if you look over past experiments, that can be created by variance, but it's all sorts of other stuff. So variance in this context refers to how spread out your customers are around the average. So again, if the average order value is 100, variance is like, well, what's the lowest and the highest customers is like $5 to $500. That information refers to variance. So it's actually about the individual customers around the average, not the average itself. If that's still a bit confusing, because it can be a bit confusing of a topic, I can send you that YouTube clip again, or I can catch up with you later about it. Does the calculator include Bayesian? No, it does not at this point. And that part of the boundary or the scope of this webinar is frequentist and not Bayesian, because it's just a whole nother ball game. So I'm sorry, it's not. Just while you guys are playing, and I'll answer the last question. There is my version of the answer. You can check, excuse me, what you got. Going back to the earlier question, when deciding the minimum detectable effect, is this where you discuss trade-offs between different metrics? I'm not going to discuss trade-offs between different metrics. No, that's not something I do here. I'm just talking about you've picked a metric and this exercise is for a metric. If that's something you want to dive into, it's probably best we follow up later. But thank you for asking. All right, let's move on. So you can see I put the conversion rate here. I put the minimum detectable effect. I'm going to need about 100,000 participants in my experiment. Cool, about 47,000 each. All right, let's get a little more advanced. We're on level 2. Just so you know, there are 4 levels. Instead of planning for sample size, now we're going to plan for this minimum detectable effect thing. And this is where you have a question of, what is the smallest effect I could detect? What's the smallest effect that I'm likely, the smallest signal that I'm likely to get a significant result for? So this is this version of the equation. Now, before I read it aloud, and why I hesitated earlier is because I like to negative everything, because this frames it as the minimum effect, like a smaller effect, because that's what I care about. I care about usually detecting smaller effects. So if I were to read this equation, this is saying, for me to detect smaller effects, I either need to accept lower power, or I need larger sample sizes, or metrics with less variance. So it's the last 2 bits that really matter, right? To detect smaller effects, I need bigger samples or metrics with less variance. And before we actually start calculating, it's like useful to think, when would we even do this? Right? I think it's natural for people to think about, how big a sample size do I need? It's a little unintuitive when I present this version, like what's the smallest effect I can detect? So the first thing to notice is power and variance are the same as before. Power is a set threshold, it's 80%. Variance, we know from some analysis or past experiment, it's an information about the metric that we're using. So we can just set them and put them to the side. It comes down to a situation where, unlike the situation before, you know you have a certain sample size to work with. And this might be the case that, sorry, I forgot who asked it, but someone asked a great question, like, how do I deal with small samples? This might be a case where you know you have a small sample. Classic example, if you have a product feature used exclusively by, let's say, 10,000 power users every day, you've got 10,000 participants. You have a sample size of 10,000 to play with. That is it. Running more, like longer, running more days, it's not going to change anything. And so it doesn't matter. There's no point trying to figure out what sample size do I need, because you know the sample size you have. Instead, you're trying to say, with the sample size I've got, what sort of effect can I detect? And if this process, which we're going to practice for ourselves, comes back and says, you need to detect a 1%. You have enough power to detect, say, a 1% lift. You might go, okay, that's not so bad. I can like start coming up with some ideas. But if it comes back and says you have enough power to detect 50% uplifts, now you've really got to change what you're doing. You either have to go, you know what, I'm never going to produce such a big splash. It's not worth experimenting here. Or you have to say, I can't waste my time with little micro optimizations and small things because they're just never going to show up in the results. I've got to do really big swings because they're the only thing that's going to show up, right? And that's how this power analysis, this part of power analysis is helping you in these situations. So in this situation, you know your sample size. You get it again from an analysis or past experiments or whatever. You should know this about your business and the domain in which you're experimenting. So put it to the test. Open the power calculator again. There is a different power calculator section for this that lets you figure out what's the smallest effect you can detect. At least in my power calculator, other power calculators will have it in a different way. Try with these data points here. While you're trying, I will share, there's no open Q&A, so that's good. I've written power of 80%. If you're using my calculator, you might have been like, where is that? It's actually in an advanced setting and it's hidden, but there's like a little cog where you can go and adjust the power and the alpha criterion if you want to play around with them. And if you're using, I have a few clients myself who use this tool pretty regularly, so you can create an account, log in, and save defaults if you're changing your alpha criterion a lot. A question came up. Suzanne, yeah, the recording will be shared after. I did mention early on, because I'm in Australia and it's my nighttime and I'm an old dad, I will be going to bed after this, but I will send it out my time tomorrow. So yes, don't worry, the recording will come out. All right, cool. This is the results that I got, assuming that I did it right and didn't screw up. So 20,000 per variant with a 1% conversion rate. That's telling me that the minimum detectable effect at the smallest uplift that have a good chance, the smallest signal I have a good chance of detecting is a 27.9% increase in that metric. That's pretty big, right? So this is where I should probably stop and think, what am I going to be able to do that's going to produce an uplift that big? Because anything else is not worth the time and effort. Oh, I mentioned the power setting. It's in these settings here, or you can see I'm logged into my version and where you can set them for your account, if that's something you're into. All right, level 3. We are, how are we for time? Good, very good. All right. Let's move on to level 3. Planning for time, the easy version. So until now, we have completely ignored time. And time is important because in the real world, we don't just start an experiment and magically get all the data. Participants tend to enter our experiment over time. We get some on day 1, some on day 2, and so on. Right? And a very common question we want to know is, how long should I run my test? Now we're going to start with a case like this. When you have participants who enter your experiment in some sort of consistent way. So this is, if you looked at how many enrollments or new people join your experiment every day, and you see a consistent pattern, like this is a consistent weekly pattern, they tend to be weekly, but maybe in your context it's different. But if you see a consistent pattern and it stays pretty horizontal, right? Like you can draw a straight line through this that goes just parallel with the bottom, then you're in the easy scenario, because we can just lean back on this equation. We can figure out the total sample size we need and then divide by the number of days or weeks it would take to get there, right? Knowing how many typically come per day or per week, right? So we just lean on the same equation as before, but we're using the fact that we know roughly how many come per day or per week to just do the math and extrapolate out. Now, my power calculator has a time version for you that does that math at just offloads that burden. If you're dealing with a power calculator where you only have access to figure out the sample size, you have to do a little extra math based on how many people you get a day and so on. So you figure that out. But here's the test you can try with. So again, open the power calculator. My one has a different version you can go to from the homepage. Let's say you got a binary metric, base rate of 2%, we'll stick with power 80%. You want to be able to detect, again, 5%, and you get about 100,000 new participants every week. Roughly how many weeks do you need to run this experiment for? I'll just check. We're all good here. While you're playing around, I'll mention this challenge I have at the bottom. I made up for this example 100,000 a week. Where would you get a better number? So this is the result that I got, again, assuming I put the numbers in correctly. If you go to the test duration calculator, we want a binary metric. We are working this out on visitors per week. We have a constant enrollment or consistent enrollment pattern. That's what this means, steady traffic. And we're getting 100,000 a week. We've got our 2% conversion rate and our 5% minimum detectable effect. It will take us about 45 days or 6.4 weeks to get the sample size we need to have enough power to detect a 5% uplift. And you can sort of see how they add up down the bottom if you open up this show traffic graph. Just quickly going back to that extra question, like I made up 100,000 a week, where would you get a better number? The best thing is to find a data set where you can look at something like this, right? So you should go back to, say, ideally, an old experiment or an AA experiment or something where you can look at how many units or how many people or customers or whatever it is enrolled in my experiment every day and plot that out. And that will tell you, for your case, whether you're getting 100,000 a week or 10 a week or 10 a day or whatever it is. So try and lean on some past data if you can. We're almost there. Level 4, planning for time, the hard version. Now, it's common that you don't have this nice consistent pattern. That's super common in like e-commerce, for example, but in many situations, participants do not enter regularly. If you look at how people are joining your experiment, you get a lot of new people early on, and it slowly diminishes, right? You get less and less new people joining, and then there's like this tail off. This is more common when you are in a business with high frequency of use context. So maybe B2B products, or you're dealing with power users. Maybe you're like, imagine Slack for enterprise, right? You get a lot of people who are there all the time, or you're dealing with an area of your business or product exclusively with power users. Social media is a classic example. Like I worked at Meta, like Facebook and Instagram, right? People are very frequently on the tool. And so you get a lot of people early on, and then it sort of slows down. So this is quite a common pattern. I don't think if you read a lot of lessons from like e-commerce sites, like I used to work at Booking.com, they always think and talk about this consistent traffic pattern, but that does not translate to many businesses. So you definitely want to figure out which of these sort of scenarios your context is. This is trickier because more time, like every extra day, every extra week, does not mean you get the same number of new people. You can't do the simple maths as before. And actually, in this sort of case, you have to think about, you could think about either of these. You could lean on the sample size approach, or you can lean on the minimum detectable effect approach. And I'll explain when to use each of these. So generally, you want to stick to this sample size equation and figuring out the sample size you need. When over time you keep getting enough new participants, even though it might tail off, it's still enough traffic coming through that you could keep running longer and getting more sample. Focus on the minimum detectable effect case when most of your participants enter quite quickly, and then that tail drops really fast, and then it's almost negligible how many people come in. In these cases, planning your runtime is you're not really waiting for sample or like sample size, because you get it very quickly. So runtime isn't about waiting for more people. Runtime is about understanding how long is it going to take for the people in my experiment to produce the signal that I care about, right? It really depends on your business. Again, in e-commerce, there's often an assumption that once someone experiences the experiment, the purchase or whatever happens on a fairly short time frame, like within hours or a day, maybe. But in many other businesses, customers might get exposed to your change, and their behavior might not change for a few days or a week or whatever it is. And this is where you need to understand your business and your customers to try and figure out how long am I going to need to wait. And that's where runtime planning is different to sample size planning. Okay, here are two of these graphs, right? Where I'm saying how many new participants come in on each of these days. You can see one's like drops off super fast and one is like tailing off, but there's still a lot of sample coming through. This is a case where we'd probably lean on, well, how big a sample do I need? Because I can just run that long. This case is where I'd probably lean on the minimum detectable effect approach because I basically get everyone by day 3 or 4 here, and then it doesn't matter if I wait longer, purely from a sample size point of view. So I'm going to suggest we put the sample size situation to the test. The minimum detectable effect is pretty much equivalent to the previous one with the caveat that I mentioned. Runtime needs to take into your business context into account. But try with sample size. So you can jump back into that same section of my power calculator. In this case, it's all pretty much the same, except I'm saying, let's imagine you have 100,000 new participants on day 1, but by day 14, you're only seeing about 15,000. How many weeks would you need to run this experiment? I'll give you 20 seconds to try and plug that in and see what settings need changing. Just checking the Q&A. Oh yeah. So yeah, you're absolutely right. Using historical data will get you those better answers. Yossi, can you clarify about the different approaches by the type of traffic you described? How will your approach change? Yeah, sure. Let me finish. I'll share the answer for this and then I'll quickly go back. So I'll try to make it super clear. So the answer to this one, again, assuming I got the numbers right, you would change this traffic pattern. Before it was constant enrollment. So there's a toggle here that says front-loaded decaying. That means it gives you the option to sort of put in 2 data points and it just tries to estimate what your drop-off looks like. So here we're saying visitors on day 1 is 100,000. By day 14, it's 15,000. This all sits the same. This can take us about 2 weeks. And you can see how visitors come in each day and how they accumulate up to, well, in this case, only day 9. Now, I'm going to quickly jump back because Yossi asked if I could clarify. I believe you're talking about this page here. Can I clarify yes, great, thank you. Can I clarify these different approaches? Okay, so on the left, let's say, it's saying I get most of my, in the first few days, almost everyone who's going to join my experiment joins. Like 95% or something are joining in those first few days. And then some people join over time, but like marginal, right? It's like nothing. So really, by day 4, I pretty much know what my sample size is going to be. There's no point in me doing the sample size equation because I know what the sample size is going to be. Like it might be 100,000 or whatever it is by day 4. It doesn't matter. Like running longer won't give me more. So instead, I should be thinking rather about the bottom equation where I go, well, I know probably what the sample size is going to be. I know the variance of my metric. So I'm more interested in figuring out what's the minimum signal I can detect, because now I can start to plan in terms of how big a changes can I make that will show up as statistically significant. In a case like this, every day I run the experiment longer, I'm getting fewer people, but it's still enough that I can go, yeah, I can keep getting a bigger and bigger sample if I run longer and longer. I mean, this is teetering down towards 0, but like even up to 3 weeks, right? I'm still getting substantial people. So here I might go, you know what? I do want to know what sample size I would need for a minimum detectable effect I care about. Let's say I care about 5% and it says you need, I don't know, what are these numbers here? 10,000, like 50,000 people, I might go, cool, that's going to take me a week to get that many people. So it's enough that I can take this approach. I hope that's a bit clearer. I'm just checking the Q&A again. I can't see it while I look at the slides. I think I got it. So on the left, you're estimating for the possible MDE, and on the left, you optimize for the sample size best. Yeah, exactly. You got it. You probably answered that while I was rambling on, so you got it. Thank you. Oh, good. Thank you. All right. I'm glad it made sense. Let's move on. So everyone got this chance to do this. Okay, now we are at the biggest reveal yet. You made it. We have covered all the like technical stats stuff in this course. I'm just going to do some recap because I think we did cover a lot. It's been, what has it been now? About an hour and 40 minutes. And that's a lot of content. So I suggest just hanging around and letting the dots connect right at the end here. But otherwise, you can sort of take a breather, relax, let your brain rest a bit. So right at the beginning, just a reminder, all results have noise. Only some have signal. And we care about finding signal and avoiding noise. Statistics helps us make the decision when we get a result between noise and signal or noise in an accurate and aligned way. That's its accurate and aligned way. That's its job, right? And it helps us by combining information to produce a p-value, comparing it against a threshold, and helping us make a decision between, is this probably just noise, or is it so unlikely to be noise, there's probably signal here, right? That's what statistics is doing for us. Because we know how these p-values work by combining these data points, we can go and plan the input, and we can play around with these levers to see how those p-values change and what it would take for us to get signal depending on various constraints in these things. And when we do that, when we go into the planning exercise, we're maximizing our good decisions, right? We're making sure that we're investing time and effort to make good decisions, and we are avoiding or minimizing making these errors, these false alarms and these time wasters and these missed opportunities. Power calculators are your best friend when you're doing this planning. They help you plan in advance, right? They help you answer things like, how big a sample do you need? What's the smallest effect you can detect? How long should I run my test? And so on. Some advice from someone who's had to go through this this in a from the ground up formula wise. Try not to let this slip, right? Try to keep this statistic knowledge alive, especially if it's new for you. So like I said, I will send the recording out probably my time tomorrow. So revisit it. If you have a team at your work who you think could benefit from this, reach out to me. Sometimes I'm usually pretty happy to do even short, like hour-long versions of this material for bigger teams. Try to publicly share something you learn. I don't know about you, but for me, when I try to explain something I learn even better. And if you're into like writing public content or LinkedIn posts, tag me. I'll reply. I will definitely get involved. I'd love any feedback. If you enjoyed this, if you struggled in parts, if you thought it was awful, whatever the case may be, please let me know. It really helps me make better content for everyone. And I'm super friendly if you can't tell through the webinar, through the camera. But hit me up anytime if you want to have a chat or meet in person. I'm in Sydney, Australia. I'm heading to Melbourne soon. I'll be across Europe and Singapore a little bit later, and then lots of travel in the future, but they're the upcoming ones. And with that, thank you. Please keep in touch. If you want to get like my really deep content, there's my newsletter. I'm super excited about some of the additions coming up. And I can see a bunch of stuff popping up in the Q&A. So I'm going to focus on that. Please feel free to just hit up the Q&A. If you want to keep answering questions, I'm going to hang around for the next 20 minutes or so and answer that stuff. But if you got to drop off, thank you for being here. Let's get into the Q&A. On the left-hand graph, so I assume we're talking back, Nikki, about those sample size graphs. I'm just going top to bottom in my thing. Do you account for novelty effects? On the right, with frequency, I'd run a test for 2 weeks when there's continuous enrollment, but account for some initial spikes if the feature is new because of novelty. Yeah, great question. So this is where there is a disconnect between the math of power calculations and the context and what can happen in your business and your customers. Um, so that's sort of what I was saying on that, like that graph you mentioned on the left, where you get almost all your samples straight away. You can get some really big spikes and novelty effects, and that's for you as a practitioner to uh, anticipate or to think about and to leverage the data you have available to you in your tool to decide whether you're going to wait a certain amount of time or anticipate whether you expect these things to plan your runtime. So there's not a mathematical solution to figuring out novelty effects and so on and knowing what to do. This really comes down to you as a practitioner thinking deeply about how your changes affect your customers. So sorry, that might not be the most satisfying answer, but I think it's a really important one. And when you know that, that puts you a level above a lot of people. Sam, when inputting your visitor volumes into a test duration calculator, would you recommend inputting an average daily or weekly volume? If so, what time period would you use? Yeah, good question. I set the toggle because it varies from business to business. I would say a lot of businesses use the weekly because they have weekly cycles and they want to always get weekday and weekend users as a bundle and they want to make it full weeks. But in many cases, some teams just want to do daily and they have more regular traffic. So it's really what's good for you. Again, I'd suggest like if the pattern is clearly different between weekends and weekdays, it's usually best to stick to a week block and use the weeks. Yeah, I hope that answers it. Arthur, if we plan to segment the results, do you recommend defining the segments beforehand and performing the calculations for each segment? And if we realize that a segmentation is complicated, like a large sample size is required, high MDE, etc., would you indicate this before the test and not do the segmentation? This is a really good question. So when segmentation is planned beforehand, when you know that a specific segment is like your target and you will be slicing or dicing the results down to focus on them, absolutely do the calculations in advance and plan for that segment. There are quite a number of cases where you might just say, I care about the results for this segment of users. I don't want to harm all the others, but I care about moving the needle for this segment. And in those cases, definitely do it. If it's more of a like, and in that case where you're trying to make the decision on that segment, right? If it's hard, then you're sort of stuck. Like you have the same problems as any other experiment where it's hard and you've got to think whether it's worth the effort. Now, if you just want to slice and dice results after an experiment to learn and explore, I don't think doing the power calculations in advance is really helpful. You can, by all means, but it's always going to be harder to get signal on a smaller sample. So as soon as you segment, it becomes harder. So I think it's what you're saying here is really nice. It's like if you know you're going to do some slicing and dicing, but you might not have enough power, and so you're not going to make a decision on that, you're just trying to learn from it. It's a great thing to declare up front and just be honest with everyone. Like, hey, after the results, we're going to do a bunch of slicing and dicing here. We might get some weird false positives. We might get some weird false negatives. We're accepting that risk and we're just trying to learn from it and we'll iterate based on that. But this is a great question. Let's move on. Oh, thank you, Roman. I'm glad you liked it. Thomas, I'm trying to convince my B2B colleagues who deal with low volume test sizes to take power into account, but I'm kind of struggling. Do you have any tips how to convince them? Convince in inverted commas. I like it. I think, sorry, I don't, it's maybe not the best way to get all this context, but part of it is, are they just running experiments without thinking about power? Or are they not into running experiments at all? Is maybe the thing, but like, I assume if you're trying to convince them to take power into account, that they're running experiments. I think the some of the best tips, this is just generic, right? I'm not saying I have great tips, but it's like try to show them try to show them power calculations and like make it easy for them. If you can help them with power calculators, like go and do some power calculations for them and come back and be like, oh guys, I did some power calculations and like your experiments here are going to take twice as long as they are maybe in this page of the product or whatever it is you're dealing with. If you can give them something useful from power calculations, that tends to move the needle a little bit. But the other thing is if they're experimenting and not doing power calculations and they're in a low traffic situation, they're almost certainly going to get a lot of neutral results. And usually when teams get that, they get demotivated. People lose faith in the testing and they like stop experimenting. So if you see them heading in that way, bring in power calculations also as a bit of a like, hey, here's something we can use to like stop the rut and try to figure out how to get around this problem. And then if they do have low power from low volume, like low samples, there's all sorts of techniques that work really nicely in B2B, like Cupid, which is something I've written about. Just hit me up for that sort of stuff. But yeah, this is a people problem, and I don't have a perfect answer. Jason, oh, thank you. I really appreciate it. I'm glad it was useful. Thank you, Suraj. Thank you, Caroline. Thanks, Thomas, again. Thank you, Aditya and Ahmed. Thank you. Really appreciate it. Alejandro, Alex, what does a great hypothesis to test look like, and what does a bad one look like? What are the key things not to miss? Ooh. So we didn't really cover hypothesis writing in this webinar, but it's a topic that I really enjoy. I think there's a whole spectrum of hypothesis formation that are valuable. If you're in a simple case where you're just getting like used to this stuff, there's the standard one. It's very simple. I think it's like by changing X, we expect Y. Like that's the simplest version. A hypothesis should be a prediction. By changing something, we expect this outcome to happen. And just declaring that as pre-registration is the most important place to start. If you can say that before an experiment and then make a decision that's in line with that, you're winning. For me, though, as you like climb the ladders of like maturity, what I love in hypothesis is a super crystal clear articulation of the problem that you believe you're solving and how the thing you're changing is solving that. So, for example, we believe customers find the payment flow confusing, and that making the I don't know, the Pay Now button more visible will reduce that confusion and increase payment rate, right? Something like that. So you've clearly articulated the customer problem, how what you're doing is addressing it, and then the metric or behavioral changes you expect as a result. And when you start to do it like that, if it fails, you go, okay, maybe the button visibility was not the thing creating the confusion. So you can iterate on the problem before you just abandon the idea. Like that didn't work. The button's not related to confusion. So maybe this time it's the copy in the payment form needs improving, right? So it starts to like thread a lot of experiments together. Anyway, I'm going to stop here because I realize I'm probably rambling and I like this topic, but feel free to hit me up if you want to discuss it further. George, how do you suggest to split groups? We need to create balanced groups, right? Based on clicking, stake activity, etc. So there's two ways I'm interpreting the question. One is, how do I decide who goes into control and who goes into test? That is almost universally should be done through pure randomization, like a coin flip. Most experiment platforms will do that for you. If you're using an in-house or you're doing it manually yourself, maybe just hit me up, but there are like hashing algorithms that do this for you. The exception to this is when you have either very small or very skewed data sets where like if one person got into test or control, they would totally blow all the results out. That's where there's a technique. I'm only going to say it so you could look it up if you're interested, but a technique called stratification becomes useful, or other techniques like capping or Windsorization. Don't worry if you don't know what these terms mean. But in general, you should be just trying to randomize. taking things like past activity into account is where stratification helps. The other way I'm interpreting the question is like, do you split, like what's the percentage split? How many people should go in controller test? Should it be 50-50? Should it be 60-40, whatever? I think it's the next newsletter edition of mine I'm publishing in about 9 days towards the end of the month is going to speak exactly about that. That's a topic I really, really enjoy. So definitely check that out. Just like jump into my newsletter to get that. But in general, the lesson of the summary of the article is 50-50 is the best way to go. Anything else is going to give you less statistical power, and it's going to make it harder to detect signal, which means you probably have to run your experiments for longer, or they're not going to produce statistical significance at all. So in general, 50-50 is the way to go. Hopefully I answered your question with one of those two. Rohini, thank you. I wanted to ask, do we read results differently if we see that the number of users in control and treatment is different? Yeah, good question. So there's, in general, no. Like, let's say you're splitting people 50-50. Like with a coin toss in the code or whatever. You're almost never going to get exactly the same number of people in each variant, right? I mean, if you get an odd number of people, you definitely won't. So that's totally fine. And the way that that gets worked out in the maths is you always divide your metric by the number of, you average it across how many people you have in the group. So you're always looking at the averages, which means you don't have to worry about the number of people in each group being exactly the same. Now, there is something really important called a sample ratio mismatch, which means that the number of users in control and treatment are actually really different and not in a way you expect. So let's say I expected a 50-50 split and I had 100,000 people all up. I'd expect something close to 50K in each group. It's not going to be exact, right? It might be like 49,700 and blah and 50,300 or whatever. But if you got like 40,000 in one group and 60,000 in another group, that's weird. That's called a sample ratio mismatch. Something I've posted about before, but it's worth looking up. It is a problem. It means there's a problem with how your tooling has randomized people and something has gone wrong, and you should not interpret the results at all. So under normal conditions with no sample ratio mismatch, it's just about using averages and you don't have to worry. But do check for sample ratio mismatch. Every team, every experiment should check for these things. I hope that helps. How best can we do this experiment in marketing mixed modeling analytics since we know that our data is almost small sample? Oh, that is a that is a totally different kettle of fish, MMMs. Realistically, so when you get to these like very complicated statistical procedures, like market mix modeling, basic power calculators are not going to be useful to you. I mean, you can like plug in some numbers as a really rough, just like back of the envelope to get a good feel. But ultimately, if you want to do proper power calculations with advanced methods, you're probably going to need a data scientist who can like run simulations for you and figure it out. So sorry, it's not a great easy answer, but it is a complicated technique and it requires a complicated solution. Prince, when's the next session? Good question. Tell me what you want next. I mean, I can run this again, but I think you probably have more questions off the back. So as part of your feedback, I'd love to hear what other stuff would be useful, and I'll go from there. Thank you, Tracy. Really appreciate it. Rohan, if an overall test result is non-significant, but significant for a segment, should you make the change live for 100% of users? Ooh, good question. And I'm just checking. Yeah, okay, we're almost there. So I'll just clear. Thank you, Prince, again. Thank you, Arthur. All right, cool. I got two more questions. So let's say you get non-significant on the total sample, but it's significant for a segment. What do you do? My opinion is it really depends whether you expected that result in the first place or not. If before starting the experiment, and I like to refer here to something called the Texas sharpshooter fallacy. I don't know if you've heard of it, but for those of you who haven't, imagine someone who's shooting, they shoot the side of a barn with a shotgun, and then they go and they paint targets around the bullet holes. right? And they're like, hey, look, I'm a perfect shot. That's what happens when you don't think about these things in advance and you get results back and then you start making decisions. You're basically um, you're fitting the data to like your decisions after the fact that you've taken the shot. Rather, the best thing to do, the most appropriate thing to do is before starting the experiment, you declare what the target is. If you're saying, I'm making this change because I think it's going to be valuable for this segment, it is not valuable for everyone, but it's valuable for this segment. Then if you get the result you're describing, it's significant for this segment, but not significant overall. That is a perfectly legit thing to do to roll out to everyone because you're saying it's good for this segment, it doesn't hurt, or there's not really any signal for everyone. It's exactly what I expected. Cool. But if you find it later, I would say, oh, that's really interesting. I'm going to think about it. I'm going to learn from it, but I'm not going to ship it to everyone because it could just be a total false positive. And I would rerun the experiment. Um, yeah, that's what I do. That's best practice. Uh, Alejandro, do you recommend running an A/B test twice to make sure there are no false positives and negatives? Yeah, cool. So I guess that's a little bit related. Another term used in the field for this is replication. Like, should I replicate my experiments? Look, if you can, it's great to do. If you can replicate, it's really wonderful thing to do. It's very powerful. The trade-off there is it's going to cost you a whole lot more time. It can create confusion in your customer base depending on like if they're high frequency of use users, they keep getting alternated between variants and it can like wash out the replication effect. So I think it's great to have in your head as something you would like to do. And if you can do it, do it. Especially as like that p-value. So a lot of teams get like very antsy when the p-value is around the threshold. It's like 0.049, right? Just under the threshold. Or it's like 0.051. It's like, oh, we just missed it. Like, don't make decisions in those cases. Replicate is the best thing you can do because if it's signal, it will show up again. That's really the case. If it's noise, it will not show up again. So yeah, it's one of those tricky ones where you have to have a bit of business context and thinking to decide when is it worth replicating. But when you can, awesome, go for it. Sam, last question at the moment. What's your point of view on using sessions or visitors for test calculations and analysis? Also, Melbourne, when you come to Brisbane. Yeah, good question. I don't have a Brisbane trip planned. I'm sorry. Okay, sessions versus visitors. This taps into a broader question around like, what should my unit of analysis be? Is it sessions? Is it visitors? Is it accounts? Is it like if you're in a B2B scenario, is it like entire organizations? Like when should I pick what? It really comes down to where you think you get the cleanest signal for the biggest sample size. So what I mean by, let's take your case, sessions versus visitors, right? I work with a company right now who have to deal with this problem. They're dealing with a subscription business and they're looking at the registration flow and they're changing around the UI and they were using sessions. I'm like, guys, think for yourself as a customer. You come in, you see one version of the product, you leave, you come back, you see another version. Like now because it's on sessions, right? Your behavior from your first experience is going to influence your behavior in the next experience because you're clearly seeing these differences. You have to randomize on the visitor level because on the session level just washes stuff out. On the other hand, let's say I was making a backend change, like a backend coding change, refactoring my code, and I believed it was going to improve site reliability. Now, really all I care is about in a session, do any errors get produced? Does the site crash? That's fine. That is a great situation where you might switch to using sessions instead of visitors, randomizing on sessions, because the effect should really only influence session per session. How site performs in one session doesn't matter in another. And you get a much bigger sample size because there are way more sessions than visitors. So it really depends on where the signal will be clean, and then when you draw that line, like how big a sample can you get? So I hope that helps. I'll have to figure out a Brisbane trip. Well, you got to come to Sydney. That's rude. I think we're done with the Q&A. Yeah, thanks, Sam. I appreciate it. So, oh, we've gone over time by a couple minutes too. So let's call it there. I really appreciate all of you joining. Thank you. And again, the recording will come out soon, and keep in touch. Goodbye, everybody.